Perhaps without further ado, I'm very, very happy to have our first AI speaker here. So if you would be interested in coming up here, Marcus Noack, thank you so much for joining us here today. We're really, really excited to hear about AI superpowers, myth or reality. You will tell us.
Okay.
Come on up here.
All right. Thanks, everybody. Thanks for inviting me. Thanks to the organizers. I was asked to introduce what AI/ML is, so I'm going to go with ML. I don't want to get into AI. But that's going to be the world and history's shortest introduction into ML. So let's see what we can do. It says pocket size. That's really what it is. So I'm Marcus from Lawrence Berkeley National Lab. My background is in applied math. But we're not going to get much into math. But let's get started. So I want to be controversial right from the beginning. It's not working. That's okay. Right from the beginning. And answer the question, what is machine learning? And straight up, there's no one answer. If you went into a seminar room at Lawrence Berkeley National Lab, all mathematicians and computer science, you ask that question and just discuss, it would take all day and there would still not be a result. This is completely my opinion, my perspective, what I've learned over the last probably 10 years. When we look at the news every day, it always seems like there is this new ML or AI thing coming out, and it seems new. It always seems new, but it turns out it's actually almost never new. What machine learning really is are advances, gradual advances over the last decades, before it was even called ML, in three things, and that is data. We heard a lot about data today, and data has to be collected in a certain way that empowers or even makes it possible to do AI and ML. There's mathematics and statistics, and there most of the methods exist and have existed for, the first function approximation was, I think, 200 years ago. And some of these methods are very much still in use, very popular actually. They're probably renamed now, and then we see a news story about it, but they're still the same algorithms. And of course statistics, and it is all about, and mathematics has always dealt with these maps. So that looks like a very mathematical expression. It's actually not. It is a map that takes something in an input space and produces something else. And when we talk about what AI/ML can do for us, it's always important to know that that thing that looks like an X, we have to think about what that is. What's our input space? Where's the data at? And what do we want to predict? What's the M? And the thing in the beginning, that is where people like me come in, making that operator, making that map. But everybody who wants to use AI/ML should know what that map, what do I want to map to what. And then there's of course computing. The first computer in World War II could do 1,000, if I'm not mistaken, floating point operations per second. Now our phone can do about 1 billion, and this is Perlmutter can do, I think, 10 to the 16, if I remember correctly. And then we have Frontier now. Exascale computer is at a bit over 10 to the 18. So these are exascale systems. So all of this has been developing gradually over the more or less recent past and has empowered what we now call AI/ML. Let's talk a little bit about more or less about data. We see on the left-hand side in the upper corner there, we see a data set we might be familiar with. Those could be coordinates in 3D, for instance. On the right-hand side, we have something that looks a little bit more cryptic. Those are so-called SMILES. This is how you encode molecules. They look pretty crazy. Lots of people could deal with on the left. On the right, it's a little bit harder. And what I'm showing you is unlabeled data. So this is data that doesn't have a label, and usually this describes some position in some space. And this is a mathematical concept, but in the end, whenever we want to do AI/ML, we always need the notion of a space. What I said earlier, where's our data? Where is it located? And in this case, when we have unlabeled data, that's all we're looking at. These are just positions in some space, something they're easy, like on the left, and something that's harder with these SMILES, these molecules. And then we have labeled data, and that is always when we have the positions, but in addition to that, we have what is then in ML called labels, which again are basically function values, and they have existed for hundreds of years, but now ML calls it labels, so that's called labels. And so there are these labels, and suddenly you see these points are elevated, so they have some quantity of interest assigned to them. And it is important to realize these basic two different kinds of data, because the main two branches of machine learning come right out of that distinction of the kinds of data. And that is on the left-hand side, unlabeled data, we do unsupervised machine learning on. And unsupervised machine learning tries to find structure in data. So it's not about any sort of prediction. We're just saying there must be often a lower dimensional representation. We could say here we have this two-dimensional space at the bottom, and we say the points are all located in there. And we can keep describing those points as they have coordinates in 2D, so that we need two numbers per dot. But we could realize, oh, there's actually a line that goes right through them. Once we have discovered that, now we can always reduce the points to only one number, dimensionality reduction. Great. This is used in a lot of places, approximating motion of a robot. There's a lot of data reduction techniques that work like that. For instance, in spectroscopy, image classification is often, but not image classification in the sense I give it cat or dog, but I just give it a bunch of images and I let it figure out what's different about those images. And if I'm lucky, it figures out there's a cat and a dog in the images. And I have a bunch of big words here that are always thrown around, and somebody asked me earlier about generative AI. That's a good example of generative AI. Generative AI means having a hugely high-dimensional space, finding some sort of structure in that space that's low-dimensional. Once you have that figured out really well, it's really hard to figure that out really well, and that's why ChatGPT sometimes screws up. But if you have this underlying surface in this high-dimensional space, once you have it, you can now take elements from it, and you have generated something that is now valid. A vaccine, a molecule, a sentence, whatever. On the right-hand side, we have labeled data. So that is supervised machine learning. That there, again, we have some quantity of interest, and we have examples. And now we want to find out what those labels are in places where we've never measured them. Climate is a great example, a big climate model. We have positions on the planet. We might have temperatures over time. And we want to figure out what happens in the future or in places where we haven't measured it. A typical supervised ML algorithm. And we see, again, some big words: regression, linear kernel rich regression, Bayesian regression, Gaussian processes. Neural networks do that too. And classification can be done that way as well. And because I only have 1 minute, I will be really quick. Again, I told you that mathematics has focused on these maps for a long, long time, but what's different now? And the difference is really good data, compute power, a whole lot of marketing. And so if I had to answer what are AI superpowers and if they are real, I would say that they are real, but not because anything particularly new was suddenly developed, but because a lot of people suddenly work on getting good data, making computing faster, working on the algorithms, and some advancements in statistics and mathematics as well. And with my last 30 seconds, I will tell you I myself work in autonomous experimentation, which is a field in AI. It needs a lot of uncertainty quantification. It is about making all the big instruments that give us new science in the nanocenters and particle accelerators around the world, really, making those experiments not depend on human decision making. So you replace all of that, the data analysis and also the decision making, by AI. It is what is called active learning, and while I have the chance, I want to clean up what that word is. Active learning is an algorithm that can choose its own training data. And it is often done, again, by uncertainty quantification. You usually go with the uncertainties really, really high, and again, some sort of space. So we always have this notion of a space. We have to always figure out what our spaces the data is embedded in. And we can make decisions based on that. Usually we go for regions of high uncertainties, and we plug this into mathematical optimization. Mathematical optimization, function optimization always plays a huge role in AI. And this is how autonomous experimentation can work. Here's just an example where Air Force Research Laboratory came to NSLS2, that is a synchrotron at Brookhaven National Lab over in New York. And here's one of those algorithms working, figuring out where only in a 2D space, very simple, but still cool, where to collect data optimally. And again, where does this AI superpower came from? There was no really new algorithm. Gaussian process uncertainty quantification has been, I think, developed in the 50s and 60s. But there was a lot of work going on to combine all these, all the different algorithms, analysis, message passing systems to make this possible. So in the end, it's the people who connect up all these advancements in different fields. And that's all I wanted to say.
Thank you. none or a million, I think it is. Yeah. Actually, you have a question, or you just? Yeah.
Okay. Hey, I used to be at Los Alamos National Lab, so we'll just so I feel like I have to make just one comment. I think one of the most important things you said during your talk, and thank you for that, was the comment that in 80 years, from World War II to now, the world's computer, the fanciest computer, went from a kiloflop, 1,000 calculations per second, and at the exascale at the national labs, it's now at 10 to the 18, right? So it's a, if I get the math right, it's a million billion times faster than the original kiloflop. So the thing I'd just like to ask you to comment on, the algorithms might be the same, but do you see something in just the sheer size of the scale, right? Because there's the concept of phase transitions and the fact that the systems can do things now that they couldn't before when they were only given a million billionth of the data.
So you mean what you can now do with AI because of the advancements in computing?
Just the scale.
The
scale is so much bigger now.
Yeah, so we recently actually had an algorithm that is the Gaussian process, uncertainty quantification, an algorithm that was always only able to quantify uncertainties at like about 10,000 data points. And so we recently broke the world record, and we ran on 5 million data points, and we're approaching 10 million now. And that needs some clever math, but it was in the end only possible because of a few hundred A100 GPUs on Perlmutter. Because in the end you have to parallelize, and you have to, there's a certain limit how clever math can get you to compute less, but only to a certain limit. At some point you just have to scale it up to these computers. So in the end, without these computers we wouldn't talk about AI and ML, I think.
Wonderful. Thank you so much.
Okay.
This was great.